This video covers Chapter 7 in EE211 Circuit Analysis 1. We will talk about analyzing first order circuits in this chapter. So far we've covered three different passive elements in this course: resistors, inductors, and capacitors. And we have introduced one active element, which is an op-amp. And so remember, an op-amp is classified as active because, for one reason, the output power in the signal is more than the input power in the signal. And that's one reason we can call it an active element. It's not to say that it's producing power, because your op-amp is powered by external power supplies, but if you look at just the signal that you're amplifying or differentiating or integrating, whatever you're doing to it, the output power will be greater than the input power. So we are going to look at two circuits in this chapter that find many applications. One is the RC circuit, so that's a resistor and a capacitor together in a circuit, and the other one is an RL circuit. For these circuits, Kirchhoff's laws still apply. Kirchhoff's laws always apply, except that for these circuits, instead of having algebraic equations for summing the currents into the node or summing the voltages around the loops, we will have differential equations instead. And that's a direct result of relationships for the capacitor inductor elements, such as I equals C dV dt, for example. That's a differential equation. And so you'll use those directly in our Kirchhoff's law equations. An RC and an RL circuit are both first order differential equations. That means that when we write the loop or the node equation, there will be one derivative involved, not a second derivative or a third derivative. An equation that has a second derivative in it would be a second order equation. So these are all first order equations that we'll look at in this chapter. We are also not yet considering the circuit's behavior with frequency, although these circuits now do have a behavior with frequency. But in this chapter, we're going to look at specifically how the signals behave in time. In a later chapter, we will look at how they are behaving in frequency with the same, even with the same input signals that we're applying in this chapter. But right now, we're just going to look at how they behave in time. So always keep that in mind. So the circuits that we'll analyze, the RC and the RL circuit, there's two ways that we'll excite the circuit. In one case, it'll be a source-free circuit. So this circuit has some kind of an initial condition on it, such as the capacitor is already charged up to some voltage. And then we will not have any independent current or voltage sources in the circuit, and the capacitor actually will discharge in the circuit, and we'll look at how the circuit behaves. There may be, however, dependent sources in this circuit. There may be some component that depends on the current or the voltage that's somewhere else in the circuit. But there will be no independent current or voltage sources. Now there must be some kind of initial conditions on either the capacitor or the inductor, or the problem would be useless. If there's no voltage or currents that are being supplied back to the circuit, no energy being supplied back to the circuit, then the circuit would not be doing anything and everything would be a zero. So this explicitly, you have to have some kind of initial charges present in the circuit. The second case that we'll look at for exciting our circuits are by exciting the circuit with an independent source, which generically we can call this problem a forced response to the differential equation, or having a forcing function in the differential equation. We will look at two cases in this chapter. One is applying a step response to the circuit, and one is applying an impulse response to the circuit. So a step response is like turning on a DC power supply or closing the switch. And an impulse response is applying a very short pulse to the circuit in time. So forcing functions, or forced response, can also be from a sinusoidal or an exponential source, but we will consider this problem in a later chapter when we start looking at the frequency response of the circuit. So here are the four scenarios that we're going to look at: a source-free RC circuit, a source-free RL circuit, and a forced response of an RC circuit and the forced response of an RL circuit. So I started to do this already because you don't need to watch me write everything, but this is our source-free, come on pen, get my pen working, there it is. This is our source-free RC circuit right here. And I don't know why the book drew it the way they did, but they had IC current going this way and IR current going that way, which I thought was a little odd because, I mean, it doesn't matter. You can solve it either way. Whatever your conventions are, you obey it. But there's really only one current in this loop. This capacitor has some initial charge on it, and there is one and only one current in this loop. So I drew them both the same way. So the capacitor has some initial charge on it, and perhaps there was a switch in this circuit that closed, and then at that point in time this capacitor will start discharging in the circuit. So as I said, there's an initial charge on the capacitor, and we'll just call that V0. And using KCL, we can write that current in the capacitor as a function of time equals current in the resistor as a function of time. So that's just KCL. I can rearrange the terms right here. IC minus IR equals 0. So then the next step is you apply the relationships. We know that I in the resistor is V divided by R, and that I in the capacitor is I is C dV dt. So it's a little bit this is related to the voltage in the capacitor, but this is related to the voltage in the resistor, which I wrote explicitly out over here. But they are the same voltage, are they not? They may be oriented differently, but by Kirchhoff's voltage law, this voltage here must be the same as this voltage here. So we have one variable here, voltage, that is the variable that's in this differential equation. So note I have one derivative right here. There's not a second derivative, so that makes this a first order differential equation. So I've written my first order differential equation just by substituting what current is from our KCL relationship. And now I can rearrange the terms. So I get the constants on one side and dt on one side, and then I have 1 over v on the left side times dv. And I can integrate both sides with an indefinite integral. And so when you integrate 1 over v, you get natural log of v plus a constant. And on this right-hand side right here, this is just a constant. So when I do an indefinite integration right here, I get the constant times t plus a second constant, constant of integration, since this is an indefinite integral. So here's where we play a few little games. There's no reason why I can't add these two constants up and move them to one side of the equation, right? So now I have ln of v equals minus 1 over rc t plus, and I'm going to add up constant 1 and constant 2 and just call it a constant. But hey, there's no reason why I can't take the natural log of the constant either also. And that's still a constant, isn't it? A natural log of some constant is still a constant. So I have a natural log of this, natural log of v minus natural log of a equals minus 1 over rc t. So natural log of something minus natural log of something else from our math rules, whoops, this is an a, is that equals minus 1 over rc t. So now what do I do next with this equation? I want to get rid of that natural log somehow. So the only way to get rid of that natural log, if I, just diverge for a minute, if I have natural log of some number, I'll just call it a b, and I have it that it equals c. I just arbitrary numbers, and I want to solve for b right here. How do I solve for b? So how I solve for b is I raise both the left side and the right side of the equation, I say e to the ln of b power and e to the c power right here. So I apply an exponential function to both sides. That's okay. Whatever I do to the left side of the equation, I do to the right side, and we're okay. So e to the ln of b equals this, and this equals e to the c. So that's how you would solve for this argument of the natural log function here. So that's exactly what we're going to do over here. We're going to raise both sides, or take say e to the both sides of this equation, and when I get that, I find that v over a equals e to the minus t over rc. Therefore, v equals a e to the minus t over rc. Move on. I need a little bit more. v equals a e to the minus t over rc. So I came a moment ago, I had that v, and it's a function of time, equals a e to the minus t over rc on the previous slide. And so recall that we had some initial conditions, that v in the capacitor at time 0 was v0. So we are going to use these initial conditions in this equation to solve for our unknown constant right here. So v at time 0 is v0 equals a e to the minus 0 over rc. So e to the 0 is, this is 0, right? E to the 0 is 1, and we find out that v0 equals a. So net result is that we get the equation for what voltage is doing as a function of time in this circuit. This is called the natural response of a circuit, and because it refers to the behavior of the circuit in terms of voltages and currents with no external sources or no excitation. So keep in mind that if the capacitor had no initial charge on it, and by the way, this is actually the voltage in the capacitor, if the and the voltage in the resistor for that matter, if the capacitor had no initial charge on it, then the whole circuit zeroes out, and yeah, so not even an interesting problem. So you have to have some kind of initial conditions on the circuit so that you can look at the natural response of the circuit. So it's how the circuit behaves in the absence of any external sources or excitation. So I did this problem for you, actually solved the differential equation, did a few mathy kind of tricks with the constants so that I got the answer in the right form, and you saw that it was an exponential solution. But the trick to doing that was playing a few games with the constants so that you got it in a nice form so you could have a nice solution in the end. So this first order differential equation is something that occurs a lot. It occurs in mechanical engineering, it occurs in electrical engineering, it occurs a lot of places. And when you get through your Calc 1, 2, 3, 4, your next course in your sequence, which not offered, I believe, in the community college system at all, but the next course will be a course in differential equations. And in the differential equations, you study explicitly all kinds of different first order, second order, with a forcing function, without a forcing function. You'll solve, you'll learn about all the solutions to those type of equations. But I'm going to step away from your textbook presentation for just a moment and show you the same problem we just did, but solving it with some knowledge of differential equations, or just a little bit different perspective to say, rather than just apply our math rules, do a little trick with the constants and get an answer in the form that we like. I'm going to show it to you a little bit differently, and what some of the meaning is behind using a differential equation. So come on, pen, come back. Sometimes my pen, there it is. Okay, so this was our equation originally, dv dt plus 1 over rc v equals 0. And that's because, yeah, so Yes, that's a correct equation because I equals c dv dt. Okay, or minus c dv dt. Okay, so what this equation really means is that you have to have some solution. You're looking for some solution, v as a function of t. You need some solution to this equation, and the solution is some kind of a function. And what it says is that if I take the derivative of my solution of my function plus a scaled version of the original function, that it has to equal 0. So you were looking for some function that solves this equation. And you'll learn in differential equations that the only kind of function that can solve this type of an equation is an exponential function. And the solution for v of t, for the function that we need that solves this differential equation, is going to have always the form. The only solution that will work here well, it's not quite the only solution, but it's almost the only solution. Is anyway a solution that will have the form generically a e to the st. And notice I didn't put any sign assumptions here or anything. So an exponential equation will solve this, will be the solution to this differential equation, guaranteed. And it turns out from Euler's formula that a cosine or a sine, which you can derive from an exponential, a cosine or a sine function is also a solution to this differential equation. But that's actually derived through Euler's formula from the fact that we have an exponential solution to begin with. So if I say, okay, I'm going to assume my solution for what v of t is doing has this kind of a form, then I'm going to take this assumed solution with unknown s and unknown a and put it back in my differential equation. So dv dt equals, now we just take the derivative of this, is s a e to the st, correct? And when we put, and then we know v is this. This is our assumed solution right now. So I'm showing you some differential equation techniques. So you put our assumed solution back into this original equation right here. And so I have s a e to the st plus 1 over r c a e to the st equals 0. So I've put my assumed solution into the differential equation and performed the derivatives to see that indeed this is a solution to the equation. And so factoring out, I get a, well, it's a linear combination of the derivative of the function and the original function. So I'm going to factor this out. A e to the st s plus 1 over rc equals 0, from which we get that either this, so you have two terms here equals 0, either this equals 0 or this term equals 0, correct? So we get s plus 1 over rc equals 0 is one possible solution, or s equals minus 1 over rc is the other possible solution, correct? Pause here. Yeah. So continuing on, I didn't quite say that right. Having this be one of the possible solutions just says a is 0, so that's a trivial solution. So this is one possible, the other possible solution, which is that, which equates to that. So now we have a solution for what s is. If I go back here, so that means that we know that v of t, our solution function, is a e to the minus 1 over rc t, which is what we found before on doing this problem the other way. But we found now that the solution looks like that. From there we have to apply the initial conditions, which is the same as before. So we knew that v at time t equals 0 equals v0. So I substitute that in here, and I get v0 equals a e to the minus 1 over rc times 0. E to the 0 is 1, and so once again we get v0 equals a. So our final solution to this differential equation is v as a function of time equals v0 e to the minus t over rc. Same as before. I just looked at it as a different approach because I wanted to attach some meaning for you to what this differential equation really means. It means that we're looking for some function v of t that solves this equation. And so from differential equations you will learn that only an exponential function will solve this first order differential equation. So I assumed an exponential function of this form. I don't know a, I don't know s. I substitute it back up into the differential equation. I go ahead and solve for my unknowns a or s, and then also apply the initial condition so I can complete the solution. So I just wanted to show you that little bit different approach to solving this from your textbook. Textbook has the full complete solution, but this is the methods that you'll learn in differential equations when you take that course. So moving on. So that equation that we just developed right here looks like it's a decaying exponential. It starts at value v0 and it decays with time. So this is what the behavior of the circuit looks like. This is what happens to the voltage across the capacitor or the voltage across the resistor with time. And this is the equation that describes that. So this value of resistance times capacitance, it's called the time constant of the circuit. It turns out that if you multiply resistance times capacitance, that will come out to be units of time. I'll show you that in a moment just to prove it to you. But our units are good. We have time, and we have time in the numerator and the denominator, and it becomes unitless, and that's what it's supposed to be. And the other thing to note about this value r times c that we call the time constant, it's sort of officially called the time required for the response of the circuit to decay by a factor of 1 over e, or that turns out to be 36.8% of its initial value. So you can see that after one time constant right here, where time constant is r times c, we get v0 e to the minus 1, which is 0.368 v0. Plug that into your calculator, you will see. So that's sort of the definition of the time constant. Oops. So showing you the units here, recall that of course resistance is in ohms, and so I'm going to prove to you that the answer is in seconds. So this is, I want to prove to you that seconds equal ohms times farads. So the only way to do that, ohms and farads, is you have to break it down into their fundamental SI units. So we deal in the SI units, which fundamentally at the base level is kilograms. SI units will be in kilograms, meters, seconds, and everything should break down into those units. Am I missing? I think I'm missing one. So let's break down ohms into that, because these are ohms and farads are called derived units. They're derived from the SI base units. So if we break them down into their amps is included. That's right. So if we break that down, an ohm is actually a kilogram meter squared amp squared per amp squared second cubed, and a farad is actually breaks down into its fundamental SI units here. So ohms times farads, you do the units cancellation, and you will indeed be left only with seconds. So keep in mind when you calculate your RC time constant that it has to be in ohms and farads and not in milliohms and microfarads or something like that, because you will get messed up and you won't get the time constant correct. So make sure that you get it in ohms and farads when you compute the time constant. So this is what different circuit behaviors can look like for different time constants. So if the time constant is 2, that means bigger component values for either the resistor or the capacitor. So bigger capacitor or bigger resistor in the circuit, and it will decay slower. For smaller values of resistance or capacitance, the time constant will go faster. So one of the other interesting things to point out in this circuit, I actually don't think that your book mentions it, but let's look at it for a minute, is that I show 5 time constants here. So this is the time constant, so that's 5 values of RC. That's the way this plot has been normalized. And the reason people like to say 5 time constants is because it relates to how much has decayed in 5 time constants. Is the circuit essentially all decayed by then? Or when we apply our forcing functions later, turning on a DC independent source, what happens after 5 time constants? When do you consider, obviously this goes out to infinity, but when do you consider the circuit essentially fully charged up or essentially fully discharged? The general rule of thumb is 5 time constants, and that is because essentially after 5 time constants have occurred, then you see that the voltage has decayed to less than 1% of its initial value. So 5 time constants, you're at 0.00674 of the initial charge of the capacitor. So people like to say 5 time constants is essentially discharged your circuit, or when we do the forcing function, it'll be when it's charged up. So let's do an example. So I sort of like this example because it gives you a little bit the bigger picture. How did this capacitor initially get charged up? Well, there must have been an independent source somewhere, and the switch is closed, and the switch is closed for a long time, and the capacitor has a chance to get fully charged to whatever its fully charged value can be. And remember, when the capacitor is fully charged up, current no longer flows in that circuit. So at that point in time, after actually more than 5 time constants have occurred, it will turn out to be, after sufficient time has occurred for this capacitor to get fully charged up, then it appears as an open circuit. It is something that cannot hold any more charge in the circuit, and it's waiting to have a discharge event. So you close the switch, you charge it up for a very long time, and then you open the switch and you see what is the natural response of this circuit. When you open this switch, no current is flowing in this leg, right? This is just a leg sticking out in the air. So when you open the switch, this part of the circuit is gone, and this part of the circuit is the part that you're going to analyze. So we need to know what the natural response is of this circuit after when the circuit gets a chance to discharge over here. One thing we don't know yet is that what is the initial charge on that capacitor, but we can find that by assuming that sufficient time has gone by, the capacitor is fully charged, so at that point it's an open circuit. So I have this condition right now, the 20 volts, the 3 ohms, the switch is closed, a long time is going by, I have my 9 ohms right here, I have a 1 ohm right here, but it's open right there. The capacitor is no longer charging, and so we just open circuit at that point in time. So the question then is, what's the voltage across here? Well, the voltage across this point where the capacitor is the same voltage that you would measure between here and here, here and here. because no current is flowing right here. So whatever voltage I measure between here and here is the voltage that's across the capacitor at that point in time. So that we know how to do. That is, I'll call that V, that's our initial condition, so V0, right? So V0 we just get from this loop that exists right here. So it's 9 ohms using a voltage divider, 9 plus 3 times 20 volts, and that will be 15 volts. So we have 15 volts across that capacitor for t less than 0, because we are going to say at t equals 0 we're going to open the switch, right? So for t less than 0 the switch has been closed for a very, very long time, and the voltage on the capacitor, the initial charge on the capacitor, is 15 volts. So that's what else is this problem asked for? Find v of t for time greater than or equal to 0. Okay, so now we have the new condition of that we're analyzing. We have 9 here, 1 here, and we have a capacitor right here that has 15 volts initially on it. And so now this capacitor is going to start discharging, but it's going to discharge into this equivalent resistance over here. So our equivalent, pretty easy right now, is of course 1 plus 9 ohms, which equals 10 ohms. The time constant would be, time constant tells us how fast this circuit is going to decay. The time constant, Greek letter tau, equals R times C, and so that equals 10 ohms times, and I better keep my units good here, 20 milliohms, which is 20 times 10 to the minus 3 ohms. And I do that math, and that is 0.2 seconds. So then I can say what the voltage is doing. Voltage now as a function of time is 15 e to the minus t over tau, which is t over 0.2. And so, yes, I think your book has it written this way, 15 e to the minus 5t. I actually like explicitly seeing the RC time constant written that way. So volts, my units are volts. So that's what the circuit is doing as a function of time. And it also says what is the initial energy stored in the capacitor. So initial energy stored in the capacitor, we just apply the formula. Energy in the capacitor initially equals 1/2 C, 1/2 C V squared. It's 1/2 C V0. It's the initial conditions squared, so you just plug in my value of capacitance and value of 15 volts there, and you will get 2.25 joules. So that's the initial energy stored in the capacitor. The other interesting example problem in your textbook is this one. Just one worthwhile point, actually, I really want to point out on all of these problems. On all of these problems, our objective is to find the voltage across the capacitor. Just to make that clear, our differential equation that we've been working with all along is giving you the voltage on the capacitor when we solve for it. It turns out that's the same as the voltage on the resistor, just opposite in sign, but so it's the same, but keep in mind that really we're solving for the voltage on the capacitor. So this problem probably exemplifies that for us. So, and also we always have to get it into what the standard form of one resistor and one capacitor. I could have capacitors in series and parallel that I have to do one equivalent capacitor, and I can have resistors in series and parallel, and I have to then get the equivalent resistance, which is what this circuit is all about as an example. So you have to get the equivalent capacitance and the equivalent resistance, and then you can get the RC time constant, and then you can mathematically describe what the natural response is of that circuit. So in this case, they have VC is initially 15 volts. How it got there, the problem doesn't tell us, but at some time where some sufficient time has been given for this capacitor to charge up to 15 volts, and then maybe the power supply is turned off and a switch is thrown in another direction, and now this capacitor has a chance to discharge in the circuit, and we want to understand how this circuit is behaving, or what its natural response is in that case. So we have to find the equivalent resistance here as compared and put it in as a series circuit with this capacitor. So that's really saying what is the Thevenin equivalent. I'm trying to get a circuit that looks like this. This is a good use of Thevenin. I'm trying to get some Thevenin resistance here to go with my capacitor. So how do we do that? So Thevenin, I'm wanting to look at the Thevenin between these two terminals, and when we find a Thevenin, you take out your load. In this case, my load is the capacitor. So you take out the capacitor and say, oh, what equivalent resistance do I see between these two terminals right now? So the first thing I see is that 8 and 12 are in parallel with each other. So 8 are in series with each other. So that's 20 ohms on this side. So I have my terminals right here. I have 20 ohms now on that side. And then also over here I have 5 ohms. 5 ohms. This is all one node here. So in reality I can move that around over to this side. 5 is here, 20 is here, 20 is there. So you can see that 5 and 20 are in parallel with each other. So R Thevenin equals our R equivalent in this case, which is 5 in parallel with 20 ohms, which is 5 times 20 over 5 plus 20, which equals, doing the math, is 4 ohms. So now we can get our time constant. Our time constant is the R equivalent times the capacitor, which is 4 ohms times 0.1 times 10 to the minus 6 farads. Ohms, multiply those two together, and my answer will be in seconds, and that will come out to be 0. I have different units here. Oh, farads, not microfarads. It's just a farads. You know, that's not a realistic unit. Having 0.1 farad would be a gargantuan capacitor. But okay, this is a theoretical problem, so our time constant then becomes 0.4 seconds. So then we can write that the voltage on the capacitor, we now have found what it does, so we're going to find that thing that we need right there, is its initial charge. It was already given to us, e to the minus t over 0.4 volts. So that's the voltage from the capacitor. Problem, where's my mouse? Problem also asks us to find what's happening in the rest of the circuit, what's happening around Vx and what's happening around Ix. So we'll continue there. So we know that we can just use a voltage divider to find what Vx is for this circuit. So Vx is Vc, and these are implied functions of time, right? And I look at the voltage divider that's occurring right there. So it's 12 over 8 plus 12. And so you just do that ratio. 0.6 times 15 e to the minus t over 0.4, and then you get the answer, which will be 9 e to the minus t over 0.4 volts. So then we get this voltage right there. Okay, good, we found that. And then Ix, it's still Ohm's law, is Vx over R. So we have Vx and we divide it by R, so 9 over 12 e to the minus t over 0.4 amps. Now we have amps as a solution. So that found everything that we needed to know about that circuit. We could have found I across there too, so it would have been VC divided by this R, and we have completely analyzed the circuit. Now we look at a first order RL circuit, so a circuit with a resistor and an inductor in it. This time the current is all in one direction drawn on here, which is nicer. So we do have an initial condition on the inductor. So when we're dealing with RL circuits, we're usually dealing with current rather than voltage. So I on the inductor, or I in the circuit initially, is I0. So that's also the I that this inductor is supplying back to the circuit at t equals 0 and when we start to look at the response of this circuit. So we do KVL for this circuit. Voltage around the inductor plus voltage around the resistor must equal 0. We do KVL this time instead of Kirchhoff's current law like we did for the resistor, because we get a nice differential equation. So remember, both the capacitor and the inductor have differential equations to describe their behavior as well as integral equations that describe their behavior. But it's nicer to work with the differential equation. So we do the substitute for VL, we get L di dt. For V in the resistor is Ri, and again we get a nice first order differential equation. We can solve it by integrating both sides like we did for the capacitor. We can also solve it by saying that we know that the only solution for this equation is of the form AE to the ST. Generic solution for I of t we know will be that form. We put it back into this equation. That's because we know that all first order differential equations have a solution equation like this. So we want to solve for what this I of t is. So we substitute it back in. So L di dt, so derivative of that with respect to time is a s e to the st. Derivative of this with respect to time is simply r equals 0. So divide, factor out, oops, sorry, it's still little mess up in there. Sorry about that. It happens. Where's my eraser? There's my eraser. Because we substituted our assumed solution for I of t into this equation. We get that, and then a e to the st equals 0. So factor out a e to the st, and then we have L plus ls plus r equals 0. So we have two possible solutions, either this term equals 0 or this term equals 0. This one would be trivial because that would mean a equals 0 and nothing is happening in the circuit. So we have ls plus r equals 0. Therefore, ls equals minus r, and s equals minus r over L. This is our time constant. So continuing on, we now have our I of t equals a. We still don't know a. E to the t, and then it's minus r over L. Or in other words, I of t equals a e to the minus t, and our time constant here is L over R, right, in the denominator right there. So this will be the definition of our time constant. Time constant will be L over R for an LR circuit. So the last thing we have to do is apply our initial conditions to get this value of A, the other unknown in this equation. So our initial conditions right here were that I at time 0 was I0. So I at time 0 is I0, which equals A e to the minus 0 over our time constant. E to the 0, anything is 1, so I0 equals A, or A equals I0. And so then we get our final equation that describes the natural response of an LR circuit. So here it is, right here. And this is the time constant definition for an LR circuit. So notice the LR circuit talks about what the current does in the circuit. So the current is initially in the inductor at I0, and it decays. And once again, in one time constant, it decays to e to the minus 1 of the initial value, which is 36.8% of the initial value. And in 5 time constants, it'll be less than 1% of the initial value. So let's look at some examples. Just they're kind of similar to the capacitor examples, but let's look. So this is the first example, that I'm going to do, 7.3 in your textbook. It's a pretty good example because it has a dependent source in it as well. Now there are two ways you can solve this problem. One is by finding the Thevenin equivalent, because I have to get it, first of all, I have to get it into the form of being an R and an L, right? And I have this dependent source in here throwing me off. So if I'm going to find a Thevenin equivalent, that's method 1, then I need to find the equivalent resistance as seen by the load, and the load is the inductor because I want to get an equivalent resistance over here. So that's method number 1. The other way that you can solve it is just take this circuit exactly like it is and write loop equations here and here, and they are differential equations, and you have 2 differential equations and 2 unknowns, current 1 and current 2, and then you have to solve for simultaneous differential equations, which certainly can be done. So I'm going to go ahead and do it both ways because this is an excellent example pulling in a lot of things that you've already learned. So if I want to find the Thevenin equivalent right here and here, and I have this dependent source right here that's dependent on the current 3I, that's dependent on the current that's right here, then I have to remove Thevenin. You always have to remove the load. But with a dependent source, then you have to put either a current source here or a voltage source here, and then find out what, if I put the voltage source here, I find out what the current is in the circuit by normal analyses means, and then I have voltage, I have current, I can find an equivalent resistance or the Thevenin resistance. So let's do the Thevenin approach first. Approach A is Thevenin. So I'm going to find Thevenin resistance to go with the inductor, and this is the load guide that these are the terminals from which I have to find an equivalent resistance. So with a dependent source, I put this 1 volt source in it. Then I go ahead and find my current, my 2 currents here. So I'm just going to write loop equations. So on the left side, I have 2I1 minus I2. That's right here in this terminal. So I1 minus I2. Yeah, okay. Plus 1 equals 0. Because it's 1 volt there. Equals 0. And there's no other resistive components over here. So you only have that middle component. That's loop 1. So from there we get I1 minus I2 equals minus 1/2. No problem there. So then we do the same thing for loop 2, and you get 6I2 minus 2I1 minus 3I1 equals 0, and you get I2 equals 5/6I1. So we go ahead and solve for that, and you get I1 equals minus 3 amps. So it's in the other direction. I0 equals minus I1, because see, I had I1 and I0 in the opposite directions. So it's 3 amps. So we found our current there. So you can also find I2 is 5/6I1. I already said that. So from there, yeah, so I2 right there is 5/6I1. So, whoops, my pendant goes away. And I2 is 5/6I1, which is 5/6 times 3. So there we go. So the equivalent resistance then, our equivalent, which is about 7 in resistance, is the voltage here divided by the current. So, right, voltage divided by current is a resistance, so it's voltage 0 divided by I0. So that would be 1 volt divided by 3 amps, so 1/3 ohms. So that's the Thevenin equivalent, and now we can get the time constant. Time constant is L over R, so it's 1/2 divided by 1/3. And at this point, keep in mind that we have an equivalent circuit. There's our L, there's our R Thevenin. This is our equivalent circuit right now, L and R Thevenin, R Thevenin, and we get 3/2 second. That's the time constant. So now we can write our equation. I is a function of t equals I at 0, e to the minus t over tau, which is I at time 0, e to the minus t over 3/2. And we were given I0 at the beginning, so it's 10 e to the minus 2t over 3 amps. That is the current through, that's I of t, that is the current through the inductor. Didn't find I of x yet. So I of x, I in x right there. So I have I0, I need I of x. Oh, we had I of x. I of x, we already have what that is. It's I1 minus I2. So this was 5/2 amp right here, and you have I1, you have I2, and you have the time constant there. So then you can find out what that, it's just a matter of substituting the values in. It'll have the same LR time constant though. Everywhere in the circuit we're going to be having that same LR time constant because that is the natural response of the circuit. So that would complete out that problem. Let's look at doing it the alternative method. The alternative method is to apply KVL directly to the circuit, and then you have two differential equations and two unknowns, which is alright, but let's do it. So we have KVL directly, so I have loop 1 and I have loop 2, so we're going to write loop equations for this loop, and this one will have a differential in it. I think I actually like solving this way better. Hang on, somebody's here. Okay, interruption there. Oh, I'm back. Need my brain back here. So we can do KVL on both these loops, except that this one will be a differential equation. So we have L, voltage here, and voltage here. L di dt plus R, which is 2 ohms, I1 minus I2, so I1 minus I2 times 2 equals 0. That's one loop equation, and then the other loop equation is 6I2, 4 plus 2, 6 plus I2, 4 plus 2, right? Minus 2I1 for this component right here, minus 3I equals 0, and from there we get that same equation that we had last time, I2 equals 5, 6, I1. So all we have to do is substitute that back up into that equation. L is 1/2, by the way, 1/2 Henry. So 1/2 di dt plus 2, this is I1, remember this is I1 because we were in loop 1, 2 I1 minus 2 I2, which is 5, 6, I1 equals 0. And simplifying that down, we get di1 dt plus 2/3 I1 equals 0. So now once again we have that same differential equation that we have been working with for this circuit. This is a differential equation of order 1. We know that the solution is going to have the form I1 of t is going to have the form a e to the st. We know that will be the form. We can substitute that back into here. That's not a 5, that's an s. We can substitute back into that equation. So s a e to the st plus 2/3 a e to the st equals 0. I can factor out a e to the st, and I have s plus 2/3 equals 0, from which we get s equals minus 2/3. Do I have some initial conditions on this? Yes, I think there were some initial conditions. I of 0 is 10 amps. And that is I1 of 0. So now we know that I of t equals 10 e to the minus t st minus, there we go. Okay, so then we found the I across the from the inductor. We can find V if we want to. V across the inductor. V equals L di dt. So substituting that in, 0.5 henries. Di dt would be minus 2/3 10 e to the minus t 2/3. And then we can find the voltage from the inductor. The voltage at the inductor is the same as the voltage right here in the circuit as well. If you have the voltage right here, you can have the current right here. So it's just ratios now at this point. The time constant remains the same throughout. Okay, so this YouTube is an hour long, so I'm going to make a separate YouTube for the step and impulse response. So this YouTube is only covering right now the natural response of the circuits. Okay, all for now.